Alright, so where we left off last time was building a table of elementary functions, functions that you should just, and the ones we put in so far, were just the power functions. Things that just look like x to a power. And the short version of the short summary of that was, if you see an odd power function, it'll look something like x cubed. It'll get like steeper as that power gets bigger. If you see an even power function, it will look roughly like x squared, but again, it'll get like steeper far away from x equals 0 as that power gets bigger. So, there's some. Let's use those ideas to start building some other functions whose graphs you might already have a pretty good idea of. Let's sketch a graph with the square root function, not by just knowing what the graph looks like, but by figuring out why it should look like that. So let's start with this. Suppose you wanted to graph the square root function, y equals the square root of x. If you want to take that and like solve it for x, what would you get?
Y squared.
Y squared, right? The opposite of square root is square root. And there's going to be one other subtlety that will wind up there. So, let's think about what this means. This graph y equals x squared. Well, I know what the graph of y equals x squared looks like. That looks like the exact same expression, but the y and the x have been swapped. So that means on the graph, just the x coordinates and y coordinates will be swapped. So, this point at 0, 0, point at 0, 0, is still a point at 0, 0. 1, 1 becomes a point at still 1, 1. Negative 1, 1 becomes 1, negative 1, and so on. Do you wind up doing that? You'll wind up with a graph like that. There's the graph of x equals y squared. And if I said that were the graph of the square root function, what objection would you make?
Square root can't be negative.
The square root itself can't be negative is one objection. What's another more broad strokes objection you might make?
It's not a function.
Yeah, that's not even a graph of a function. It fails the particle line test. So, what's the walk around? Well, exactly what you said. Y is the square root function, so that y can't be negative. And let's see what that means. So that means I should take this exact same graph, but only shade in the portion where the y values are positive. So the square root function, y equals the square root of x, starts at 0, 0, and then follows the same track as x equals y squared. That seemed pretty good. Nice. And so there's the reason that the square root function looks the way it does. It's because you try to just swap the roles of x and y's, because it should undo the squaring function. You get something that's not a function. And so you just have to fix it, make it a function. Throw out the negative y values, that'll do the job. Think we could do something similar for the cubing function? Let's try it. So if you want to get the graph of y equals the cube root of x, we'll start with the graph of x equals y cubed. Alright, so I guess that should look like y equals x cubed, but then you swap the role of x and y. So, start by just remembering what the graph of y equals x cubed looks like. Qualitatively looks something like that. So take that exact same graph and swap the role of x and y. So instead, it'll look something like that. So there's the graph of x equals y cubed. Does that pass the vertical line test? Cool. So we don't need to throw anything out of the range. It is also the graph of y equals the cube root of x. And let's see, so that meant that to undo the squaring function, you need to deal with this fact that like the squaring function is even. So when you swap the roles of x and y, you fail the vertical line test, so you can only use like half of the graph. Odd power functions don't have that issue. And let's just see if this pattern continues. Let's play this game to sketch the graph of y equals the fourth root of x. And let's start with that. Start with y equals x to the fourth. What does its graph look like?
Like a tighter parabola?
Yeah, like a parabola, but tighter. Kind of more squared off on the bottom. But at the quality of cartoon graph I'll draw, it's hard to like see that distinction. So there's the graph of y equals x to the fourth. Let's also get the graph then of x equals y to the fourth in pink. So that should look the same as the thing I just graphed, but like y and x values swapped. That the graph of a function? So what should I do? Throw out the negative y values. Fourth root is by convention the positive choice. Similarly, if you want the fifth root, well, it'll just be the whole graph. Feel pretty good? Nice. So let's read off some things from these pictures. So let's just qualitatively get the sketch. Various root functions. So it looks like all of the even root functions. Will all qualitatively look similar. They'll all look basically like the square root function. Maybe they'll get more squared off close to the origin. But otherwise they'll all just look like the square root function. The odd ones will also all look pretty similar. And let's just use those cartoon pictures to answer some questions. Even, odd, neither, or both. If you take any of these even root functions, do those functions look like they're even or odd or neither? Even? Odd? Neither. Cool, well, let's talk through it. How do you check if a function is even? Using a graph? Let's remind ourselves that we
So if it's across the, if you yeah, symmetry across the y-axis.
So if you flip it across the y-axis, you should get the exact same graph back. And this is because for a function to be even, f of x needs to be the exact same as f of negative x. So let's see. If I take any of these even root functions, and I take that and I reflect it over the y-axis, do I get the exact same graph again? Nope, I get a totally different graph, right? I get like that. So, I'll ask again. These even root functions, are they even? Folks say yes. Let's ask a similar question. Are they odd? Are they neither? Good. And let's check for oddness. How do you check if a function is odd? And I have a bullet point. If that's what even means, then what does odd mean? Yeah.
Like if you rotate on the origin, it doesn't reflect it. It would be the same if you rotated an origin.
Yeah. It is symmetric over the origin. Meaning if you pin down the origin and rotate 180 degrees, you'll get the exact same graph back. And what does that mean analytically in terms of the formula?
Negative out of negatives.
Yeah, it says that if you make the input negative, you also make the output negative. Cool. So, let's check this. So, pin down the origin, rotate it 180 degrees. Did that give the exact same graph again? No, it gave like something different. It gave like that graph. So if p is even, then the pth root of x is neither even nor odd. What about the odd root functions? Take a look at this graph. Would you say the function whose graph is that is even or odd or neither? Think for a second. Even? Odd? Neither. Cool, yeah. Pin down the origin. Rotate 180 degrees. Does that look like the same graph as you already had? Nice. P is odd. Gives you that the p through function is odd. Let's talk about intercepts next. So where are the intercepts of these functions? Where do they touch an axis?
0, 0.
Just at the origin? Nice. You know what, let's keep this split. Where are these functions decreasing? Let's break this up into cases. Where is this function decreasing?
Never.
No. Or what about when p is odd?
Never.
Also never? As x gets bigger, the y values always go up. So, where are they increasing? And let's do this one, this one has a more straightforward answer. When p is odd, when does that graph look like it's increasing? Does it ever fail to be increasing? No, I mean, it's never decreasing, so if I asked you when this thing is increasing, what would you say?
Negative infinity to positive infinity.
Negative infinity to positive infinity? All real numbers? Something like that? Alright. Even root functions.
0 to infinity.
0 to infinity. Including 0 or excluding? want to include. And I'm not gonna like the endpoints issue is always a little bit subtle and I don't want to focus too much on it. But if you start at 0 and start traveling to the y, the y values immediately start going up. Yeah, so that's why I wanted to be included. Neato. So there's a bunch of elementary functions. There's one more that maybe I want to introduce right now, even though we've already seen it. Absolute value function. So you've seen the graph of absolute value. It looks something like that. Absolute value of x equals x if x is bigger than 0, 0 if x equals 0, negative x if x is less than 0. Maybe we'll even color code this a little bit. That line gives you this bit indicated in blue. That condition gives you that part of the absolute value function. Are those green and blue exactly the same color?
Not really.
Oh, okay, good, good. So let's look at this graph now and answer some questions. Even or odd? Or neither?
Oh, it's reflected, so it's even.
Yeah, it looks like it is its own reflection over the y-axis, so it should be even. Alternately, even means that it just doesn't care if you stick a negative in as an input. Does absolute value care about negative signs? Yeah, so it better be even. Ooh, did anyone think about the question of what is the one unique function that is both even and odd? Cool. Let's compute domain and range. Looking at that graph, what's the domain? Yeah, it looks like you can plug in any real number. And at the same time, is there any number you can't take the absolute value of? Nope. These instructions apply for everything. What about the range? What are the valid outputs for absolute value?
0 to infinity, including 0.
0 to infinity, including 0. All right, so yeah, it looks like all of these y values, no matter how big they are, the positive ones are all in the range. Looks like that changes at 0. So 0 to infinity, 0 is included because an output of 0 is achieved when x equals 0. Intercepts. Goes to the point 0, comma 0, there's no other place where it touches an axis. Cool. That feel pretty okay? Alright, so we have this pool of elementary functions to pull from. You know what the graph of the p through function should all look like. You know what the p power function should look like. You know what the absolute value function looks like. I guess you also know what all linear functions, what their graphs look like. So there's like a pool of functions we can pull from. Let's talk about building new functions from them.
So the absolute value function is increasing or is it decreasing?
Ooh, let's see. At that point, would you say, if you only saw that much of the graph, would you say the function looks increasing or decreasing there? Decreasing. It looks like y equals negative x. So, oh yeah, those are there. I was just not going to do it. So it looks like it's decreasing on negative infinity until 0, and increasing on 0 to infinity. And how do you check that? Well, if you want to know if it's decreasing on this interval, only look at x values that are less than or equal to 0. If you only saw that much of the graph, would you just say it's a decreasing function? If you only saw that much of the graph. Yeah, that looks decreasing. It's going down for all of the things you can see. If you only saw non-negative x values, would you say that looks like an increasing function or a decreasing, or sometimes up, sometimes down? It's only going up on that interval, so it's an increasing function from 0 to infinity. Cool. All right, so let's start combining these ideas with some algebra. Let's start transforming functions. So our next goal yeah, let's use the square root.
Cut off on top, yeah.
Nope. So our goal is to graph things that look like maybe, let's leave that positive 2, negative 3x plus 1/2 minus 7. Figure out how to graph things that look like that. So you take a function whose graph you know, and you do some linear stuff outside of the function. Nope, inside of the function. And then you do some linear stuff outside of the function. You should be able to figure out what that does to a graph. And here's the idea we'll use. Well, it looks like I just need to know what happens when you add a number to a function, when you add a number to the input of a function, when you multiply an input by a number, and when you multiply the output of a function by a number. And then I need to combine those things together. So let's start with this. What should happen to a graph if I add a number to that graph? What just seems intuitive?
Origin moves up.
Yeah, whatever it does at 0 should move up. And in fact, all the y values should move up. Shifting up by c. And let's see a quick Desmos demo of that. Give me a value for a positive constant that you would like to add to a function. 3, good choice. Let's see, I'm going to allow that thing to move. Maybe I'll let it take that range. Let's take the square root function just because that's the one I wrote on the page. So there's the graph of f of x. That looks like the same as the blue function, just shifted up by 3. Nice. And let's make this smaller. I think I want both things up. All right, so if adding a number shifts up, what do you think subtracting a number from a function will do? Shifts down. And let's just see if that holds up. There's this function minus this number c. Does that look like it's just been shifted down by c? Cool. What if I add a number inside of the parentheses? I hear a call for shifting to the left. Anyone want to say shifting to the right? All right, cool. Well, that's saying shifting to the right would seem like something really intuitive to think, though, right? Somehow what we'll see in the next couple days is whenever you do something inside the parentheses, it does the exact opposite of what you expect. When you add a number c inside of the parentheses, you will shift left by c. And let's, again, just see that happening. Has that shifted the graph of the square root function left by c? Nice. And I guess we can even let this parameter c vary. Yeah, that just looks like it shifts by however big c is. So what should happen when you subtract c?
Shifts from it.
Shift to the right. It should do the exact opposite. Cool. So, we have these rules. When you add a number inside or outside of the parentheses, this tells you exactly what it should do to the graph of a function. So let's start with a function that we know, and let's use this idea to sketch the graph. What does the graph of f of x equal x squared look like? Or rather, just like draw it on your paper. You know what the graph looks like. It's like a parabola. Its intercept is at 0, 0. Maybe you can track that it goes through the point 1, 1, and negative 1, 1. This is definitely not required for the particular exercise, but I'll make sure to get those points correct. Negative 2, 4. All right, so there's the graph of f of x equal to x squared. How would the graph change if I wanted x plus 2 quantity squared? Yeah.
You would shift the graph to units.
You would shift the graph 2 units to the left. Cool, so let's do that. Point at 0, 0, it becomes negative 2, 0. Both of these points shift 2 to the left to x value negative 3, x value of negative 1. That point at 2, 4 becomes 0, 4, and negative 4, 4. Vito, that seem okay? F of x plus 2, so that would be f of x is x squared, then add 2. What would that graph look like?
Just move up two units.
Yeah, take the exact same points, move up 2 units. That'll add 2 to all the y values. Cool. All right, so we have these 4 moves. If I want to start graphing things that look like this, then it looks like I don't need to just like do those moves, I also need to like think about doing a combination of them. So let's do a combination of them. Let's start with the graph of the square root function, because this one says to start with the graph of the square root function. And let's make this the goal. Let's sketch the graph of y equals f of x minus 2 plus 1. And let's do it one step at a time. And we'll notice that like we can do these steps, we'll think about orders of steps. So let's deal with one or the other first. Should I deal with the minus 2 first or the plus 1 first? Folks from minus 2? Folks from plus 1? Folks who say the order doesn't matter in this case? Yeah. I think so. But let's do it then this order first. I think minus 2's had it when I asked which one to do first. All right. How do you get the graph of f of x minus 2?
Go right to.
Go right by 2. Awesome. Cool. Now I just need to deal with the plus 1. What does that do to the graph? Up 1. So this point at 2, 0 will become a point at 2, 1. Cool. Let's just see what would happen if we did those in the opposite order. Because sometimes these order issues will make a difference. If I wanted, well, you already told me that shifts the graph up by 1. So let's take this graph, shift it up by 1. See this point at 1, nope, 0, 1. To go from here to there, how should I shift the graph?
Left by 2.
Say louder?
Left by 2.
Left by 2, excellent. But I don't want that. I want a minus 2 there. So you answered the question I asked, but not the question I should have asked. Cool. And yeah, it's the exact same graph. The order of those two moves doesn't actually make a difference. People feel pretty good? All right, so let's go up to the example, motivating example up there. We want to be able to graph stuff like that. So right now, I know how to deal with like this plus 1/2. I know how to deal with that minus 7. It looks like I still need to deal with multiplying the input by a numball and multiplying the output by a numball. And we'll build towards that in a few steps. Let's first think about just what happens if you multiply the input or output by a negative sign. Let's just think about what that does, and then we'll deal with like the fact that that 3 is a 3 and not just -1. So, I don't know. Do people want to spend time and do another example of what we've done so far on their own? People think they'd benefit from it? Cool. Not seeing any demands? Let's think about what happens when you stick a negative sign either in front of the variable in the parentheses or in front of the whole function. And let's just see what people's intuition is. If you stick a negative sign in front of the input value x, what do you think that should do to the graph? Yeah.
Does it reflect on the y-axis or like flip?
I think that seems sensible. In fact, I agree absolutely, that's right. Why? Cool. Your answer is absolutely right. Yeah, you will reflect over the y-axis. And if you like, the reason is the same as the reason that evenness means that the graph is symmetric over the y-axis. If you go and make the input of a function negative, well, what does that do to the graph? It just makes all of the x coordinates negative, or positive if they used to be negative. It changes the sign of all the x values. Yeah, that's reflection over the y-axis. And maybe I'll say it one other way. Make all x values, not make, multiply. Multiply all x values on the graph by -1. And cool. What if I want the graph of negative f of x? What do you think that should do?
Across the x-axis.
I think reflect across the x-axis. Right, f of x is like the output values, that's like the y values on the graph. So if you make all the output values negative, that's like making all the y values negative. Yeah, that's reflecting over the x-axis. And that's because you need to multiply all y values on the graph by -1. And if you like, I'm including that second sentence because with some frequency, I will accidentally say, we will now reflect over the y-axis when I mean we will reflect over the x-axis. But I mean, you multiply the appropriate x or y values by -1. So let's see this. Let's see this in practice. Here's the graph of a function. X cubed minus x plus 1 is the graph of this function. Computer generated. So if you wanted the graph of negative f of x from that starting point, how would you get it?
You would flip it over the x-axis.
You would flip it over the x-axis. You would do the reflection that makes all y values negative what they used to be. So let's track them one at a time. I see this point here at 0, 1. Where does that go on this new graph? Yeah. 0, -1? Cool. I see this point up here. It looks like it's -1-ish, 1-ish. Where does that point go after you do the reflection?
1, -1-ish. Or would it be the opposite?
So only the x values, only the y values will get multiplied by -1. So the x value will stay the x value, the y value will become negative. So there's this x-intercept at like 1 1/4-ish, x equals -1 1/4-ish. What will that become when you do this reflection? Stays the same. X-intercepts don't change when you do this. Which I guess makes sense. X-intercepts are when the y value is 0, -0 is 0. And then all of these y values that become super negative now become super positive. Does that seem sensible? Nice. So there's the graph of y equals negative f of x. What if I wanted the graph of f of negative x? Could you do that? Yeah, do it. And then we'll qualitatively talk about it. I think I'm going to ask you for the y-intercept on this one, the x-intercept. I'm going to ask you for those coordinates, and some of them you'll have to be pretty approximate. Yeah, that clock is fast. All right, so how do people feel? Do they have the y-intercept? Where is the y-intercept for this new graph? 0, 1, the exact same places it used to be? Oh hey, if I give you absolutely any graph, when you do this operation, will the y-intercept ever change? No, because you multiply x values by -1 when you do this. Y-intercept doesn't change. X-intercept. You have to be approximate because you don't have exact information in the original.
It's like 0, 1-ish.
0, 1-ish. It's like, you mean 1, 0-ish.
Yeah.
It's like that point, but you make the x value negative.
Okay.
So it's like there-ish. All right, x-intercept done, y-intercept done. Tell me about any local maxima. And I think I want like the point where it happens, so x value and y value.
.51.
0.5, 1-ish. So like that, but you make the x value negative. It already was negative, so it becomes positive. Cool. So 0.5-ish, a little bit bigger than 1. All right. Cool. Local max, check. What about a local minimum?
-0.5. -1.
Yeah. So like that point, but make the x value negative. Cool. That exercise feel pretty okay? Cool. And the numbers didn't work out particularly nicely, but that's okay, sometimes they don't. And you couldn't even really tell me what they were on the nose. So let's close with one last thing about this example. Do those two graphs look the exact same? No, they don't. What does that tell you about the original function? Yeah,
But it's not odd or even.
it just tells you it's not odd. It's also not even. Because f of negative x is not the same thing as f of negative x. Those two things are not the same, so this thing is not odd. I guess we can also see this. Does f of negative x look like it has the exact same graph as f of x? Nope, so it's not even. But those two graphs look pretty similar, right? They're just like, there's a vertical shift separating them. So it's like pretty close to being odd in some sense. Cool. Feel pretty good? All right. So one last example. I have 5 minutes left on the clock. Let's put these ingredients together. So let's suppose I want to ask you, what does the graph of negative x plus 3 quantity squared plus 4 look like? And let's break it up into intermediate steps. Let's deal with the negative sign first. Y equals negative x squared. Then we'll add the 3 in the parentheses, then we'll add the 4. But I guess that means you have to start with y equals x squared. What's the graph of x squared look like? Parabola has its intercept at the origin, opens upward. All right, so what does the graph of negative x squared look like?
It's the same thing.
Is it?
It opens downwards instead of upwards.
Yeah, because we need to reflect it over the x-axis.
Oh, I see, that's my game.
The negative's outside of the parentheses. So reflect over x-axis. Cool. And maybe I'll continue to track that this point here is at 0, 0. All right. Next step. What do you do to get the next thing in that list?
You shift it left.
Shift it left 3 times. Should we also check the y-intercept? I mean, this is like a preference question. Would you like that computed in this graph? Okay, then let's do it. Let's just track, also it's going to open downward. To get the y-intercept, you plug in x equals 0. So where is the y-intercept of this graph? Zero, negative 9? Cool. And I haven't included any like scale information, so I can just put that wherever. All right. Finally, plus 4, what does that do to the graph?
Shifts it up.
Up by 4. So let's just take both of those points, move them up by 4. So this point that used to be at negative 3, 0, will be up here at negative 3, 4. That point at 0, negative 9 will now be at 0, negative 5. And we'll see a nice parabola. So I indicated that like I picked a particular order to do these in, right? I dealt with the negative sign first, and then I did the shifting. Do you think that order is special in any way? And to see that, let's actually just see what happens if I do these in the wrong order. So I'm going to do something wrong on the board with my remaining 2 minutes. with fall. So let's deal with the 3 left and fall out fall. So far, so good. The last thing left is like what's left over the x-axis, right? Is that the same as the graph that we saw was correct? No. So the order does matter quite a bit, and you can see why this is wrong if we name these intermediate steps. If you go 3 left and fall up, that's x minus 3 squared plus 4. When we reflect over the y-axis, I put a negative sign in front of the whole thing. So this new function is negative this function. And so we see why it'll wind up being wrong. You need to distribute that negative sign, so the plus 4 will become a minus 4, which I didn't want. So there's an issue with ordering. We'll hammer it home solidly next time. But right now you can check whether your steps seem reasonable by just thinking about what each step actually did. Cool. I have my office hour later today. This class does not meet Tuesdays, so if I don't see you during my office hour, I'll see you on Wednesday. Say that out? Certainly not on me.
I'd left, so I just did February that I don't think I did today.
Okay.
But my paper on the 6th,
Oh yeah, that's as long as it's like readable and I can like as long as it's readable and I can tell what you mean, I'll be forgiven if I'm like I mean you see the quality of graph that I generate by
Right.
I'll expect something that's like readable that I can make sense of. If you look at it and see, well that like looks bad, you can then describe it in words, maybe even include like a decimalist footnote. Yeah. Yeah. Yeah.
I was wondering, is there a time we could set up to meet, or like if I could turn my like homework in late, because I need help on it, and I was gonna come on Friday, but Fridays are my cleaning day, and I had to clean before I had to babysit, so I like was on the verge of being late to
Okay.
babysit house. So, but I need help with it, so.
How's your 8 a.m. tomorrow? Yeah, let's do that.
Okay.
Yeah, and I get that it's like annoying because it's only in the morning. but-
I have class at 11, so it's like. It blocks.
Yeah, 8 a.m. is like the most reliable time for me.
Okay,
So
yeah.
we can meet tomorrow, and then when you do turn in the homework that's on in, just remind me to ask for the reason.
Thank you.
Just want to make sure I was marked here.
Oh, yeah, I saw when you, Chris Crawford, right?
Yeah.
Yeah, I got it.
Thank you.
Yeah.